The purpose of derivatives is to use information about a function to determine how quickly a function is changing. This idea is super useful in tons of fields, but to demonstrate, I'm going to use something to which everyone can relate. So let's suppose that I'm running a race, and we have a function f of t, which describes how far I've run as a function of t. And let's say that t is measured in minutes, so f of 30 is how far I've run in 30 minutes. And let's say I start off strong, I'm running very quickly for the first 30 minutes or so. Then I start to slow down, and I only run half as far over the next 30 minutes. Then I realize I dropped my hat and have to run back, and that takes me 15 more minutes. Now at this point I'm tired, so I just lie down and I fall asleep. Let's graph how far I've run as a function of time. I'm moving quickly for the first 30 minutes, slower for the next 30, backwards for the next 15, and then I'm not moving at all. If we look at this graph, we can qualitatively describe some of what's happening as so. Our goal is to mathematically quantify these terms and to measure how quickly I was traveling. To this later point, the idea is that if we know f of t for all t, I should be able to find my speed at any given time. But how do we go about doing this? Well, recall that we can compute the average speed by looking at the total distance that we've traveled and dividing by our total time in transit. For example, if we travel 100 kilometers over 2 hours, that's an average of 50 kilometers an hour. We'll use the average to approximate our speed. All right, so let's pick a time to find my speed. Let's say that I'm going to choose, say, the 45-minute mark. And I'm going to approximate my speed over the first 15 minutes, which I'm going to denote with a little variable h here, in which case the average speed that I've traveled can be computed as so. The numerator here is the distance that I've traveled in that 15 minutes, right? It's the distance I traveled between the 45 and 60-minute marks. The denominator is the time I spent traveling that distance, 15 minutes. But 15 minutes is a pretty rough estimate, and I think I can do better. So let's look at the 5-minute approximation. I get the same formula as above, but this time all the 15s are now 5s. Now there's nothing special about 15 minutes or 5 minutes, so let's shorten this even further. The 1-minute approximation is like this, and the 30-second approximation corresponds to when t is 0.5. The hope, then, is that by taking better approximations, that is, by letting h go to 0, that the limit will result in the instantaneous speed. And that leads us to the following definition. If f is a function, then we say that f is differentiable at x0, if the following limit exists. And you'll hopefully recognize this as the difference quotient we were dealing with above. If this limit exists, then the value of the limit, denoted f prime x0, is said to be the derivative of f at x0. Now there are two definitions here. The first is what it means for a function to be differentiable. The second is the value of the derivative if we know that the function is differentiable. Okay, let's do an example then. Let's determine whether the function 2x squared minus 4 is differentiable when x equals 3, and if so, let's find the value of its derivative. Now we don't have much to work with, so let's plug everything into the equation for the derivative. And I'm not really doing anything here other than plugging x0 equals 3 into the equation. And in this step, I know that f of x is 2x squared minus 4, so I'm going to plug that in. Now the next bit is pretty much just algebra, but we need to expand that 3 plus h squared term to see what happens. Okay, I want to pause here and point out something interesting that's happened. So we need that h in the denominator to disappear, since we can't divide by 0. To do this, everything in the numerator must have an h term in it. But these pesky 18s are in the way. On the other hand, they conveniently just happen to cancel out one another. Okay then, so continuing with the calculation, we now have something which is continuous in h, so we substitute h equals 0 in, which gives us our answer 12. And we conclude that f is differentiable at 3, and f prime of 3 is equal to 12. Another similar but different example, let's see if 1 over x minus 1 is differentiable when x equals 4, and find the value of its derivative. Once again, we're just going to throw everything into the definition. Using the fact that f of x equals 1 over x minus 1, we get this. Now let's simplify the denominator here. I'm going to do the work on the side just to make our lives a little bit easier. Again, there's some convenient canceling, and if we plug this back into our formula, we get this. Now this double fraction is gross, but remember that dividing by h is the same as multiplying by 1 over h, giving us this result. Finally, canceling the h's gives us something that we can plug h equals 0 into, giving -1/9 as our answer. Now later we'll develop tools to make these computations simpler, but for now we just have no choice but to use the definition of the derivative.